Let's now look at how we could improve the motor response by adding in derivative control. We never use derivative control alone. When we use it, we will always use it along with proportional control. So we'll start out with the equation that we used for proportional control, where the voltage is equal to a constant times the error. We'll then add on the derivative part. We'll have another constant, this one called KD, and this is times the derivative of error. Since we'll be implementing this equation in our microcontroller code, we won't be able to directly calculate the derivative of error. We'll approximate it like this. We'll say that the derivative of error with time is equal to the current error in position minus the last error in position. That is, what the error in position was the last time we went through the control loop. And we divide this by the amount of time that it takes to get through one loop in our code. Let's think for a moment about what the effects would be of derivative control. If the motor is moving towards its target position, then the current error will be less than the last error. So the numerator in this equation will be negative. That will cause us to reduce the voltage that we would have had with only proportional control. The amount by which we reduce the voltage is dependent upon how much the error is being reduced each time through the loop. In other words, the faster the motor is approaching its target position, the more we subtract off of the voltage. This has the effect of slowing down the motor if the approach to the target position is too fast. If the approach to the target position is not very fast, then we won't subtract as much off of the voltage, allowing the motor to move faster towards the target position. Also, consider what happens with derivative control when the motor is overshooting the target position. When the motor overshoots the target position, the current error is greater than the last error. However, both of these values are negative. As a result, the voltage applied to the motor becomes more negative. That causes the motor to be pulled back towards its target position at a greater speed than it would have if we had only proportional control. So let's take a look at what the effects are of derivative control on our response curve. When we add derivative control to our controller, it doesn't have much effect on the rise time. However, it does have a dramatic effect by reducing the overshoot. Increasing the value of KD also has no significant effect on the steady state error. Thus, increasing KD primarily has the effect of reducing the overshoot. Because reducing the overshoot is the primary effect of increasing KD, derivative control is also said to be adding damping to the system. Now, remember what we said the effects of increasing KP were. When we increase the proportional control, we reduce the rise time and reduce the steady state error, Those are good, positive effects of increasing Kp. The negative effect of increasing Kp is that we increase overshoot. When we add damping, when we add derivative control, the only significant effect is that we decrease the overshoot. So, with a combination of proportional and derivative control, we could combine them to achieve a desirable response. Now, the last kind of control that we haven't talked about yet is integral control. Let's look at integral control for a moment. Like derivative control, we don't use integral control all by itself. Instead, we always combine it with proportional control. For integral control, we have a constant Ki, and that constant is times the integral of the error over time. Once again, we're generally going to be implementing this in the code of our microcontroller, so calculating the integral isn't something we can generally do. Instead, we're going to do it like this. Each time we go through the control loop in our code, we will keep track of a value called error sum. That error sum will be equal to its own last value plus the current error times the loop time. Then we'll calculate our voltage by multiplying Kp times the error, and we'll add on a multiplication of Ki times the value error sum. The reason why we use integral control is it's a way to deal with steady state error. If our motor has some amount of error that is not going away over time, as it would if there's steady state error, this value in the voltage that comes from the error sum will increase over time as the motor sits in a position where it has some steady state error. Eventually, the value of the voltage will be high enough to move the motor into its correct position. So let's take a look at what is the effect of integral control on the response curve. When the motor first starts responding, the error has a fairly large value, and so the amount of voltage that comes from integral control adds up very quickly. The effect of that is to decrease the rise time. Now, because the motor is moving more quickly at the time when it arrives at the target position, integral control will also have the effect of increasing the overshoot. However, the reason why we use integral control mostly is because of its effect on the steady state error. Use of integral control can eliminate steady state error because when the response has steady state error, that error will add up over time and increase the voltage sent to the motor. So overall, the effect of increasing Ki is to decrease the rise time, increase the overshoot, and to decrease the steady state error. In the last video of this series, we'll look at putting all three of these types of control together in order to get one equation that we use to convert error into voltage.